Welcome, friends. Let's talk about the concept of linear independence versus dependence for complex exponentials. This is pretty easy to visualize. So imagine you're given e to the it. So if you're doing math at this level, perhaps you know this is cosine t plus I sine t. In other words, if you think of a circle object, so let me see, a circle object, that means a circle like this, then e to the it is just you can imagine it's like an arrow that moves on the circle this way, see? It's moving on the circle, the tip of it. Okay, never mind like the fact that I'm doing this, my hand is not steady, but you get the idea, right? It's moving on the circle. Okay, so in other words, you can imagine it roughly as like a vector. And the horizontal component is cosine t, the vertical component is sine t. Now imagine you have another one, so for example, like 2e to the it. This is very similar to e to the it in the sense that this is just 2 cosine t plus I2 sine t. The only difference is there's a 2. Okay, so what does that mean? That means it's the same thing really. The only difference is like the arrow is twice as long. That's all, you see? But it points in the same direction. In other words, if you look, it's just 2 multiplying cosine t plus I sine t. But that's just e to the it in the first place. So the 2 just makes it twice as long. That means, in other words, that e to the it and 2e to the it, we would say are linearly dependent. LD, linearly dependent. So again, let me stress, right? This is e to the it. This is 2e to the it. Now, in this particular case, if you do the real part of e to the it, for example, okay, or the imaginary part, just break it up into it's really an imaginary part. So the real part of e to the it would just be, in other words, the real part of this expression cosine t plus I sine t. So just extract the cosine part, cosine t. The real part of 2e to the it, if you extract that, that would be the real part of 2 cosine t. That's a t there plus I2 sine t. Look what happens when you divide the real parts here. In other words, imagine you do the real part of 2e to the it, okay, it, and then you divide by the real part of e to the it this way. That's just dividing 2 cosine t, in other words, you see. In the end, that's all it is, something simple, divided by cosine t, but that's just equal to 2, you see. It's a constant ratio. That tells you that the real parts, which are real functions of t, right, waves, not arrows like that anymore, but waves, that those are linearly dependent also. So we can graph those, okay? As a reminder, when you do the real part, when you apply that operation, then you just get cosine t, which is a wave. I'll zoom in a second. And then 2 cosine t, which is also a wave. Okay, you see what they look like? Let me zoom in. That you see the green graph, which is 2 cosine t, is just the black graph multiplied by 2 at each x. That's all. So the ratio is a constant value, right? If you wanted to, you can even graph the ratio in here. 2 cosine t divided by cosine t. You see, that's just a horizontal line. It's always constant, equal to 2. The same relationship holds for arrows that represent the complex numbers e to the it and 2e to the it. The red arrow is just twice the green arrow for every t that you input. So then in general, we'd say something like, if you have, so e to the it, and then you have some other complex number for each t given by re to the it. This way, regardless of the value of r, so r is kind of like a constant. Maybe it's 2, maybe it's 1/2, whatever, maybe it's 1. So if you divide them, you have e to the r, e to the it divided by e to the it. There you go. So that gives you a ratio equal to r. So in this more general case, I suppose you could visualize it by doing something like the following. Again, it's a circle. Imagine e to the it is the basic unit quantity that moves on the circle this way. Okay, let's stop it, say, in this position. Then, depending on the value of r, you get different cases, like this right here. So this would be, say, r is greater than 1. Okay, so that means you would be multiplying e to the it by a number more than 1. You're stretching it out. Let's see, another case might be something like this one here. Okay, this one right here. So that's the blue one. So that would be the case, for example, of like r being, let's say, less than 1. Then you would be taking e to the it, and just because the r, the number in front of it is less than 1, you're compressing and you're making it shorter essentially. And in all of these cases, right, the constant ratios are, the point is, these are linearly dependent quantities. One way to think about it is the arrows that make up the complex numbers fall along the same line. That literally is what it means to be linearly dependent. Or if you extract the real parts, you see, then one is a multiple of the other. That means the ratio is equal to 2. Or if you extract the imaginary parts. So one more time to finish up here, right? If I took the imaginary part of e to the it, so going by what we did up there is basically the sine function, sine of t. Extract the imaginary part of re to the it. So that would just be equal, for example, to r sine t. So now just divide one by the other. It doesn't matter, like the sine over the r sine or the r sine over the sine. You're going to get a constant ratio in either case, right? That's all that matters. So that's really it for this one. If it's been helpful, please leave a like. Thank you. I'll see you in another video.